Hi everyone, thanks for having me. Thanks for the invitation, Fabian. And today, as you see by the slide, I would like to convince you that sampling is a good idea. And in particular for Bayesian deep learning, which maybe some of you know, maybe some of you are not so familiar. But before I dive into that, very few notes about myself. Who am I? I'm Emanuel. I'm a PhD student at the Munich Uncertainty Quantification AI Lab, which is quite a mouthful, at LMU, and a junior member of the Munich Center for Machine Learning. My focus is on Bayesian neural networks, and in particular on sampling-based inference for them. And I've also been in industry before, so I've built very different things, learning to rank applications, financial risk models. It's definitely something that is very distinct from both the talk before, which was great, and also the talk today. And my background is basically in math, and all of this, what I will present also today, is of course not just my work, but it's a strong collaboration. So I would like to just give a short shout out to my great collaborators. Kudos, I didn't mention all, but I've been very fortunate to work with great people around the whole world on these problems. And yeah, thanks a lot. Also students of mine. Nice. So first of all, a motivation, just to get you going and not stop listening throughout. So I would like to start kind of spoil what's in for you first, which is performance. And by performance, I mean two distinct types of performance, actually. So before you dive into the plots, I would like to distinguish two things. The performance you might have in mind when you talk about performance is something like accuracy, F1 score, predictive accuracy, point accuracy. We can bring that to the table, for sure. So RMSE is definitely a measure for that, which you can see on the right plot here. And the second one is also uncertainty quantification, which is one of the major motivations for actually going for a Bayesian deep learning approach, which is, for instance, measured by the log point-wise predictive density, which is shown on the left side. It's better if this one is high. For RMSE, it should be low, right? And we got a couple of different methods for this. I've even seen that you talk about uncertainty quantification a few Datageeks talks before. Some of the methods were actually mentioned there already, and I think we can do much better by now. And these methods, some of them are even like 10 years old. So I would like to update the beliefs here in a Bayesian fashion, maybe. So we got Laplace approximation, mean field VI. We will talk about these methods later, no worries. And deep ensemble, which is more or less an industry standard. And then we got sampling, and we got something that we called Bayesian deep ensemble, which is basically hybrid sampling plus ensembling. And this one basically beats all of the other methods by quite some margin. So I would like to give you that as kind of the why you should listen, and then we will step by step kind of uncover how this works and why you should care in more detail. But one step back, I guess some of you don't even know what Bayesian deep learning is all about. So let's kind of give a short recap about what's Bayesian deep learning, and don't worry, it won't be super technical. I'll try to keep it rather high level and on an intuitive note. So you got your standard neural network. We're really going back to the basics. And an MLP with some inputs, and you got some output. And what we have visualized here are in these blue numbers. These are just the parameters of the network, right? You have some affine transformations, some nonlinearities, and then in the end, you get an output. And what we do is we optimize those in a frequentist way. If we now go to the Bayesian neural networks, we actually treat them as random variables. So we're not interested in a single fixed value, but we actually want to learn a distribution over these parameters. And what does it mean to learn a distribution over parameters? Now, really the only slide with formulas, and it is quite easy, I guess. So we're interested in the posterior distribution, which is the probability of the weight distribution of the weights. The W is here all the parameters of your network, and you can see quite directly this approach is quite generic. It doesn't matter if you have a multilayer perceptron, which is very easy, vision transformers, CNNs, ResNet, GPT models. All of the things that I tell you about just applies to all of these type of models. So it's quite generic. And we condition on some data, right? Because we are the Datageeks. So that's the posterior. It gives you the distribution of weights. So you can interpret it as the distribution of models. So how likely is a model given our data? And then we got the likelihood. If you have a regression task, the likelihood is Gaussian. If you have a classification task, it's categorical. This is basically fixed based on what kind of task you have. The next one is the prior distribution. This is the prior beliefs you have about the weight distribution. I'm not sure if any one of you has prior beliefs of how weights of, let's say, a GPT model should look like, or for each of the weights in very large models. We will talk about that in further detail later on. But usually you just assume a standard Gaussian for each weight in the whole network. And whether this is reasonable is something we will also cover. And the bad boy of Bayesian deep learning is then the evidence, because in nonlinear neural networks, this is intractable. So we cannot just compute it, and this is the why. But why should we care about this quantity? What does this give you in practice? And the thing is actually not the posterior, which most of you are probably interested in, but the posterior predictive density, which basically means that if you got access to this posterior and you sample from this, all of these approximate or Bayesian deep learning models basically gives you samples, so models, likely models, is if you have this, then you can, if you have a new instance, if you want to predict, if you want to perform inference, you can actually not only get one prediction out of this, but you get a whole distribution over your prediction. What does this give you? A lot of control about what you do next with the prediction. So you get credible intervals for free. You can abstain from actions in, let's say, agentic systems, but all different kinds of decision processes that are data-based, right? So you can actually quantify uncertainty and build that, get that kind of built in. And you get that via an empirical average, which is then called Bayesian model average, over these different models or samples from the posterior distribution. So the whole reason why we do all of this effort to get this posterior is actually that at inference, if we predict new data, we have a lot of basically a powerful tool to quantify uncertainty. And also from my research background, we actually also understand how these models work much better. But this is probably for the practitioner not so interesting after all, as long as it works. Right? But basically we got both of these things. So actually understanding this object also better allows us to improve training techniques for different kind of networks. So how can we actually approximate this thing if I told you this is intractable? Well, there are a few things I want to glimpse across a few of those. So first, map estimation. This is just a single point, right? So basically this is more or less equivalent in many cases to just optimizing your network. This is the most crude approximation you could do for this whole thing, and obviously also doesn't give you any uncertainty at prediction time, right? So in fact, super crude, but can be viewed as Bayesian if you put a Dirac prior on this model that you've optimized, by the way. So you can think of it also as a hierarchical thing, which people, very influential researchers, let's say at NYU, Andrew Gordon Wilson, uses this analogy quite often, and I like it a lot, that this intractable problem of approximating the posterior, you can basically view it as a way from the most simple case to slightly more evolved approximations. Next one is variational inference. Basically what you do is you take a family of distributions, a parametric one, that you know the form of, so you can parameterize it. Let's say you say it's a factorized Gaussian, because that's quite tractable. That's then called mean field variational inference. So instead of 1 million parameters, you have 1 million scale and 1 million location parameters of a factorized Gaussian. And instead of learning the weights by optimization, you learn the parameters of the distribution. Of course, this is a restrictive assumption that the posterior is just a factorized Gaussian. And actually also optimizing these things is quite nasty because the gradients are high variance and so on. So it actually also takes quite a lot of time. I'm not a big fan. Then you can also take your map solution and just put a Gaussian on top of this local approximation, which is also very convenient, quite stable, and very scalable. You put basically a Gaussian at your optimized map solution. So let's say you have a map solution, and then you just put a Laplace approximation on top. You can ensemble these methods quite nicely, and this often boosts performance. You can also, if you opt just ensemble pre-trained models, this is just a deep ensemble, and this is one of the most used and also strongest method to actually do this in practice, because it's super easy. You don't have to change your routine. If you can train a network once, you can also train it twice or 5 times, and then you get basically a agreement and disagreement between the prediction, which you can see as kind of model uncertainty, right? But this is not a true Bayesian approximation, but comes quite close. So this is kind of the spirit of what I've shown you before. So just reframing the Bayesian inference task as an optimization problem, right? But as you might have guessed, there's one more thing you could do, and it's actually directly sampling via MCMC. So Markov chain Monte Carlo, in this case, it is basically a method that doesn't require the normalization constant, so the evidence, and you get directly the samples. The approximation, obviously, of this density is then implicit rather than explicit, right? Because you have an explicit distribution if you have fitted a Gaussian with variation of inference. You can evaluate this at each and every model that you might find. And the sampling gives you samples as also visualized here on the graphic. But these samples, in essence, are exactly the thing that you need to get the predictive posterior density, which is the same for all of these methods. Because what you would do in practice at inference, if you would want to get the uncertainty, let's say, from a Laplace or a variational approximation, is you would have fitted this high-dimensional Gaussian, you would sample from it, get the predictions, and basically be at the same point as for MCMC. All right, sampling via MCMC. Now, please help me with the video, and I hope it actually works. I thought actually, yeah, that doesn't look too good. Okay, no, doesn't work. That's very unfortunate. Okay. Then, okay. Apparently it doesn't work, right? Okay, maybe the internet connection again, because this was actually part of a YouTube video. What I wanted to show you, no worries, let's try to get your imagination going, so the question I want to ask is, well, why is it not mainstream, right? Have you heard of people sampling neural networks? Probably not many of you, right? The thing is, I want to show you the loss landscape visualized from a Llama 3 model. So if you think about the loss landscape of neural networks, they are highly non-convex, super wiggly, and also not convex. So basically, you can think of them as if you go into the Alps and you just look at the surface. If you stand on top of one, let's say, Zugspitze, and you just look into all of the mountain ridges, this is basically how a neural network loss landscape looks like. And what you would like to do with the posterior is you would like to approximate all of the different ridges, characterize this whole landscape, right? Which seems impossible. So why should you even care? And I would like to make the point that you should. And it gives a lot of nice things. I would like to encourage you to, maybe on your own, check out on YouTube loss landscapes of neural networks. There are amazing visualizations. It's just mesmerizing. So just try that out. And basically the same applies, because if you think about loss landscapes, it's just a negative log likelihood, right? And the log likelihood basically perfectly goes in line also with the sampling. It's inherited, because the only thing that changes is you put a log prior on top. But the whole complexity of the likelihood transfers to the Bayesian deep learning task from deep learning. All right. And the thing is, why actually people don't use this is because there are a lot of common myths and misconceptions. Some of you might have never heard this because you haven't even heard of Bayesian deep learning. But basically, the most common perceptions, and might also be questions that you yourself asked, that questions you asked yourself while I was presenting here. Well, there cannot be a meaningful prior and weight space, right? How can you set a meaningful prior belief on a million-dimensional vector? Then it's too expensive. Markov chain Monte Carlo, if some of you have worked with this, maybe some guys with backgrounds in physics or dynamical systems, are pretty known to be expensive, small scale only, impractical, due to this intricate geometry induced by singularities. Also symmetries are part of my research that make the landscape you want to navigate quite distinct. And there are also a lot of myths and misconceptions about that. So what people assume often is this infeasible gold standard, because in the only, what I didn't say, MCMC doesn't have any assumptions, right? It basically is guaranteed to give you the correct posterior asymptotically if you have infinite compute. But all the other methods are quite restrictive in their assumptions. So it's kind of the gold standard. Everyone wants to have it, but no one tries it. And even basically, if you apply it out of the box, it's actually true. It won't work. It will be slow. It doesn't scale. So how can we actually tackle this? And I will show you a few tricks that are not so difficult after all to actually make this possible, these performance gains that I showed you in the beginning. So first myth, there are no meaningful priors. Now, finally, I also got some fancy plots for you. So the thing is, these simple isotropic priors like a Gaussian and everything, they actually, if you look at recent literature, also part of our work in our group, you can actually see that they align with optimization. So L2, everyone knows probably. If you have a standard weight regularization, the Gaussian prior actually corresponds to this. There's a very close correspondence between Gaussian priors and L2 regularization. And then if you also mesh this with overparameterization theory, then you can in fact prove that there is layer balancedness. A lot of phenomena emerge in these overparameterized, highly high-dimensional neural networks. And basically what people thought the posterior would look like if you would sample a lot of samples is because they looked at tiny toy examples that are not realistic neural networks in practice, like this underparameterized one. You see the perfect symmetries. It's very difficult. If you think about characterizing this distribution, it's horrible, right? You would not want to do this. In fact, if you look at the right one, at the overparameterized one, this is a real neural network you would maybe also use in practice. And in fact, if you both of these two are 10 million posterior samples that we've computed with quite a lot of effort. And you can see that actually the right one perfectly aligns with the prior. So the prior might actually be not so bad after all, because it actually shapes, even in these very high dimensional problems, the posterior. And we argue that it actually makes the posterior more well aligned for sampling after all. So actually the high dimensionality of the problem in deep learning is actually something that goes quite well together with these simple isotropic priors. Now, next one. It's too expensive, but is it? So let's look at those two parts of the slides, one after the other. We just denote runtime in minutes. Just trust me, for the left one, all of these methods perform really well. The deep ensemble, the DE, is basically the baseline. This is just classic optimization. How long does it take you to optimize a certain neural network? And then some of you who have worked on sampling before know maybe the U-turn sampler, nuts. This is Hamiltonian Monte Carlo based. This is considered state of the art for sampling. And if you see the overhead in terms of runtime over the optimization, you can see that there's like a 10-fold price toll that you have to pay if you want to sample those neural networks. But ours, I will tell you what the secret sauce is on the next slide, is on the same ballpark as the optimization and like 10 times faster as the state-of-the-art U-turn sampler. So actually, you can be quite fast. If you can optimize your neural network, you can also spend the same compute on sampling it, right? So it's not too expensive after all, maybe. Then you might argue, well, there are these other approximations, and they need less compute, right? And we can see that, in fact, this is a rather small scale example. We can see the red bars, which represent time, runtime. So the higher, the worse. And the blue bars are the performance and uncertainty quantification performance. And if we look at the bars, mean field VI and Laplace give really poor performance. So we directly rule them out. They are fast, but really bad. The deep ensemble actually works very well up to a certain degree, but cannot really match the performance of the Bayesian deep ensemble, which is sampling based. And even if we invest the same or even more amount of runtime into the deep ensemble baseline, which is of course easy to implement, but also takes time to optimize, basically the deep ensemble, even with more runtime, cannot match the performance and uncertainty quantification that we get out of sampling. So is it too expensive after all? If you care about uncertainty quantification, then you're actually faster to get to a certain uncertainty quantification performance. And also what I should mention is for larger examples, like really large neural networks, also mean field variation and inference, for instance, for due to the gradient variance that you exhibit, often requires more or the same amount of runtime than the sampling that we employ. So hopefully convinced you that it's not so expensive after all. But why so fast? We got novel samplers. And this is again a mouthful. We are, for instance, working with this novel sampler that's called microcanonical Langevin Monte Carlo. And it just appeared 2 years ago, more so maybe 1 year ago. So it's actually quite new. And basically, we haven't encountered a single, I'm very fortunate to work with the one who actually built it. And the slide is stolen from him, so kudos, Jakob. So the thing is, it's just, I don't want to bore you with the mathematical details. It's a lot of fancy math that enables you to be much more precise and scale better to high dimensions. But just in a nutshell, if you are familiar with Hamiltonian Monte Carlo, you basically simulate a physical system where your particles are your neural network weights, and you evolve this system. And what you do in canonical HMC, you need some momentum resampling. You have this classical interpretation as the momentum, basically a drift term and the diffusion term. And what microcanonical HMC does, it does the same thing, but just restricted on a single energy surface, which is kind of visualized here on the right plot. And this allows for more deterministic sampling and also much faster sampling. And even there are results that under certain conditions, MCLMC can complete the convergence of MCLMC is completely independent of the dimension, which is important. Basically, it rules out under certain assumptions the curse of dimensionality. Because before I told you that obviously we need a sampler that can work with high dimensions, and the prior and the overparameterization make the posterior more well-behaved. So if you combine this with a sampler that cannot work in high dimensions, it doesn't work. So basically the combination, why also we were so fast before and got even the same or better results in the slide before, is that we basically combine a sampler that scales much better than state-of-the-art samplers before, and we combine this with these high-dimensional overparameterized networks. So that's one of the ingredients. Next ingredient, we allocate the computational budget wisely. Because when we do sampling, there's a Monte Carlo error. The Monte Carlo error basically comes from not having infinite compute. And what classical Bayesian statisticians would tell me is, well, run really long chains, right? Sequential chains for good mixing. Well, if you look at this performance heat map, where darker is better, you can see that the y-axis, which is the number of parallel chains you run, so basically exploration and the exploitation in the number of samples, you see that this is linear and there's a log scale on the x-axis. So you get a lot more bang for your buck if you invest more time into parallel compute. So basically, the sweet spot is kind of here somewhere in the middle, you need both exploration and exploitation, but exploration gives you a lot of benefit. So what we do in most cases is we start off with a warm start. So you don't want to start from random initialization. Samplers are not very good at exploring there. You just do classical optimization. So basically you optimize a deep ensemble in parallel. And then you start local exploration with a high performance sampler and sample short chains, ensemble all of these models, and you got a great high performing model ensemble that gives you good epistemic or model uncertainty. Yet another ingredient, software. And this is for PyTorch lovers. So you can also plug and play with this package, ready to use, very well tested. And it also features variation inference Laplace, which my stack is fully based on JAX. So if I do sampling, I do it with JAX. But I also, obviously, to write papers, you need baselines. So Postgres is a great way to also get those baselines in. Then soon, also shout out to two of my students, Angelos and Vironas. They are currently in the final stages of writing an sklearn compatible Bayesian deep ensembles package. So for specialized on tabular data, we'll probably pretty soon also release a nice package that scales to these really large models. The thing is, the package of these two guys is also all powered by JAX, by the way, to ensure that it's really fast. So basically the same software is behind that. Small scale only. One more misconception. I was actually too lazy to maybe give you some nice visuals, but maybe this anecdote will kind of showcase where we stand today. In 2021, Ismailov et al. At NYU had a really good collaboration with Google, apparently. I love the research, and they used 512 TPUs for weeks. So basically spent a lot of money to sample a single ResNet 20 model with about 10 million parameters. Seems like a pretty big effort. And basically what we can do, we can basically get the same or comparable performance sampling for 2 hours on a handful of GPUs now. And so we've come quite far, I would say. And just some more examples. So Sam, who is also called Sam Duffield, presented the Postgres package and also presented some benchmarks with it. He fine-tuned an 8 billion Llama 3 model, so you can also do LLMs with this. And I should say that it worked better, right, than the classical Adam-based optimization. We also scaled it up quite recently. It's still under review. For 22 million vision transformers, we have done NanoGPT, all kind of models, MLPs, Paulin et al. Also this year at AI Stats sampled the CNN for 73 million parameters. So this is certainly not the scale of classical Bayesian statistics that you know before. So we're really pushing the limits, and basically it's really my takeaway is if you can optimize the model, you can also sample it. If you follow a certain recipe that we, of course, in much more detail cover in our papers and upcoming papers. But let's say, for instance, for example, the vision transformer actually took me longer to configure it to optimize correctly than the sampling. So also saying that regarding the hyperparameters of these methods, the hyperparameters of optimization, also the optimization-based posterior approximations are sometimes much more harder to get around, but maybe that's just me. So the vision kind of is the following, making sampling feasible for the overall crowd, democratizing this method, and it's basically a plug-and-play thing, right? So it's not just, as you have seen from the examples, you can use it for MLPs, you can use it for regression classification, even for text generation. You just have to apply the sampling after all. Now, all problems solved. Should we just now, from today, start sampling all of our neural networks? I still want to have a job, so it's not always yes, but I would just like to guide you through a few questions that might come up, or at least they are in my head a lot of times. So does it yield samples from the true posterior? Still an approximation, right? We have asymptotic guarantees, but I can only say maybe, because it's still an approximation. Is it more flexible than all the other approximations? Yes. Does it seem to give a better performance? Yes. And also what some people have suggested is that you need thousands of chains because this problem is inherently multimodal. What we can confirm for a couple of architectures, be it an MLP or for distributional regression or a resonant 18 model on CIFAR, 10-ish chains visit all the functionally relevant modes, and with functionally relevant, I mean the modes that are relevant to max out these predictive uncertainty quantification metrics for downstream tasks to make it actually really usable in practice. Does it yield valid functional uncertainty? Apparently it does. Also, the credible intervals are very well calibrated, which is always good to know if you are keen on doing uncertainty quantification. Is it better than restrictive optimization-based approximations? I hope I convinced you. In fact, they are. By the way, also Monte Carlo dropout was presented in one of the talks recently. We're also better than that. And is it better than vanilla ensembles? I've shown you that even with the same amount of compute, we're often far better in terms of the performance, especially in the uncertainty quantification metrics, and also can have an edge even given an equal computational budget. Does it scale? It increasingly does. Just to give a small anecdote, when I started my PhD and also my first paper, the usual networks we were considering, and I've waited with some niche approaches for days and weeks, were in the scale of 100 to 1000 parameters, which is quite tiny. And we've now scaled this up to quite huge amounts and very relevant networks in practice. So we're working on that in a very hard way, and a lot of research groups are actually doing that. And what about inference speed? This is actually a common problem between a lot of methods in the approximate Bayesian inference domain, is that you have to take all of these samples into memory, right? Which is costly. A usual paper of mine often requires multiple terabytes of storage, because we also do excessive experimentation. But overall, you have to do a lot of forward passes to actually get this empirical distribution at prediction time, the predictive posterior. But this is basically the same for all of these methods. And if you have a sensitive application or an application where you require the uncertainty quantification, this is most likely worth it. And you can also optimize these things and run embarrassingly parallel. So if you have parallel cores, this is not a huge cost, to be honest. But I've worked in industry and know that latency is an important thing. And that's why we're working on speedups, right? So you can distill the posterior samples. There are works distilling, compressing those, and this can basically speed up inference cost for like a factor of 100 or even more. I still haven't published anything in that direction, but my proof of concepts look very promising. But also other related research groups have already published some ideas in that direction. So that's something we're certainly working on. So now the takeaways. So following these presented recipes, I've omitted some of the details. Sampling neural networks should be feasible after all for many applications. It's pretty fast to run. I hope I busted a few of the myths and misconceptions. It's quite easy to implement, in fact, if you think about this Bayesian deep ensemble approach, especially in a functional API with the packages like posteriors. This is quite easy, and it provides state-of-the-art uncertainty quantification and even boosts predictive performance. So it's not just uncertainty quantification, but even this is shown to improve generalization basically also a little bit. And from time to time, actually, we have cut the RMSE for some problems in half. So not bragging, but it can boost also the predictive performance by quite a bit in a few tasks. But of course, there's no free lunch. It also differs depending on the task, whether this approach is worth it. If you are interested in this, happy to talk. Of course, we got references on our Google Scholars, on our website, contact info, blah, blah. So I guess you're all able to find those. And some of the results that I kind of teased are still not maybe published, but hopefully within the next months. So thanks a lot for your attention, and really happy to take any questions.
Thank you, Emanuel. What a nice talk.